Hello everyone, and welcome to FMC Teck Talk, a lesson from our neighbors. My name is Carmen Lowe Wasserman, and I will be your MC today. FMC Teck Talks is a new venture for FMC Canada, and we are very happy that you are able to join us. We started FMC Teck Talks to provide an education-based platform with a firm mandate to educate and bring value to customers regarding agronomic topics and solutions. They are product agnostic and cover all aspects, actives, brands, and companies that participate in Eastern agriculture. This webinar was recorded on March 3rd. I'd like to welcome Drake Copeland and Nick Hustetti as your speakers today. Gentlemen, the virtual floor is all yours.
Alrighty, well, thank you and good morning, everyone. I'm Nick Hustetti, so I work in tech service and I cover Eastern Missouri, Illinois, and Western Indiana. I've been with the company for right at 8 years. It's been a lot of fun working for FMC. We're fortunate to be involved in development and discovery of some key molecules that will hopefully help your growers become more profitable. So my training is in weed science, and this subject is very near and dear to me, and I'm definitely looking forward to the discussion. So I'm going to turn it over to Drake for his introduction.
Thanks, Nick. So I am also a tech service manager for FMC, and I cover Eastern Indiana, Ohio, and Michigan. And much like Nick, my background is in weed science. Basically had several projects based on resistant Palmer amaranth, which is a close cousin to what we're going to be discussing today. And really, that's just staying ahead of water hemp. And I think the whole idea is, in Canada, you are starting to see populations of water hemp that are escaping your current control tactics. So I think really the whole scope of this presentation is to show you what we're trying to do, specifically in the Midwest, but also there are some things that you need to be aware of that are going on currently in terms of new herbicide-resistant biotypes. So we'll go ahead and I will get started with the presentation. So when we talk about herbicide resistance management and managing those weeds effectively, you've probably seen some of the tactics that are listed here from your own university extension weed scientists, like a Peter Sikkema. So as we go through this presentation, we're going to talk about ways to reduce soil seed banks, why that's important, starting clean. We always talk about rotating modes of action or crop rotation. Cutting rates is something that we want to stay away from, but also being timely in post applications are another way to stay ahead of herbicide resistance. Me and Nick are also going to talk about utilizing pre-herbicides and other ways that maybe we don't pour out of a jug, other concepts. So ways to maximize crop competition, especially when we're dealing with something like water hemp, and then integrating a non-chemical practice. So cover crops have been a really well-studied thing here in the U.S., and I believe it does have a fit. Just depends on the farm where we can place it. And then I think the most important part as we go through this presentation is understanding that we really can't have any tolerance for escapes through the season after herbicide or weed control tactics are deployed. So the Weed Science Society of America just had a meeting this past week, and usually in these meetings, it's a good time for the scientists to get together and discuss new findings throughout the country and North America. But I want to bring up that we've had tools to get us through to where we are today, but tools like dicamba and 2,4-D that we can apply post over soybeans. In this image, you're looking at cotton, are no longer effective in parts of the country. So this is actually in Western Tennessee, where a grower applied Tavium, which is a premix of dicamba and S-metolachlor, along with Roundup Power Max or glyphosate. And this is just a very isolated population, but you can tell that the Palmer amaranth, is turning its face towards the sun and will continue to grow and ultimately produce seed. But there are biotypes like this that all across the Midwest. We're starting to see suspected populations in Nick's territory in Indiana, Missouri. We know we have populations of Palmer amaranth in Kansas that are now resistant to dicamba and 2,4-D. So it's just something to be aware of that's going on in the U.S. I think the one that really under everyone's skin in terms of weed control is the glufosinate resistant population in the Mississippi Delta of Arkansas. This is much like the dicamba, it's very isolated, but this is a population where if there's problems that are going to exist that haven't existed before, usually happens in this part of Arkansas. And this is just a rate titration of glufosinate. But if you look, as we move from left to right, we move from basically a half X rate all the way to 2 gallons of Liberty herbicide or glufosinate going out and still having survivors. So this is kind of the latest and greatest information in terms of what resistance Palmer amaranth has evolved to. And usually, unfortunately, when we see it in Palmer amaranth or water hemp, it doesn't take long for one to catch up with the other. When we think about developing a weed management strategy, we have to understand what our driver weeds are. I have a few listed here. This is something that me and Nick both deal with in the upper Midwest. When we look at Canada fleabane or mare's tail, we both have water hemp, Palmer amaranth in pockets, and then giant ragweed is also another problem for us. And really, the main issue we have is when we look at our planting window or when we're putting a crop out, that's when these weeds are also germinating, but also causing issues in terms of getting a crop into the ground. We've done a really good job in the U.S. of implementing a fall burn down strategy to take care of mare's tail or Canada fleabane. But where we're having issues is the at-planting herbicide applications, where sometimes Mother Nature doesn't allow us to make the right decision, and we end up not putting out a pre-herbicide, and it just ends up causing an issue throughout the season. And that's some of the things I'm going to talk about through not only my part of the presentation, but also Nick's. So here's a snapshot of the number of unique cases of herbicide-resistant weeds in really the upper Corn Belt, but we also have Ontario represented here. But you can look throughout the upper Midwest and see that there's quite a few unique cases of herbicide-resistant weeds. With Ontario, you're looking at 38 different unique cases of herbicide resistance, and that spans across around 18 to 20 weeds. So you guys are very aware of what herbicide resistance is and those weeds that cause you issues year in and year out. But I just wanted to give you guys a snapshot of what maybe you look like compared to other states in the U.S. And obviously, you know, this is not just a North American issue. Global increases in herbicide-resistant cases have been on the rise. A lot of that in North America has been derived from the introduction of Roundup Ready soybeans, where we were relying on one mode of action for a number of years and ultimately blew through a bunch of herbicide sites of action to get where we are today. So before we really start this discussion about herbicide resistance, we really need to understand how it happens. There's a lot of opinions out there that believe that herbicides create the resistance. They believe that if you spray a weed so many times that the plant actually creates a mutation to fight that herbicide off, and that's just not the case. When we're talking about herbicide resistance, specifically with something diverse as a water hemp or a Palmer amaranth, is those individuals are already out within populations. So their genetic structure is already there to be resistant to a herbicide. It's just the amount of selection pressure that we put on a population actually will expose that individual to go on and produce seed and ultimately have a progeny that is resistant to that herbicide application. So in this example, you see that, you know, for example, say glyphosate controls this population in the left box where we're getting, let's just say 98% control, and we have one that survives. And we continue to use glyphosate. And over time, the progeny that's resistant to glyphosate continues, and we ultimately end up with a huge problem. Now, you guys are probably thinking of an example in your own field where this happened, but that's actually how it happens when we're looking at it from a field spectrum. Another way that we can amplify the selection for resistance, besides just using one site of action, is using sublethal rates. You know, a lot of times growers go out with weeds, and as well as you know this, with water hemp and Palmer amaranth, and the label says 4 inches or less or 3 inches or less with this 1x herbicide rate. A lot of times, due to costs and other expenses, growers sometimes think that they have small weeds so they can reduce that herbicide rate and get by. But that's not the action that we want to take, because sublethal rates of a herbicide will remove those more susceptible individuals, but the ones that are tolerant within that population will go on and survive and continue to reproduce and ultimately produce seed that is more tolerant to that herbicide or resistant. Another one that, you know, we like to poke fun at a lot of times, but there's a lot of factors that go into not making a timely application. So say, you know, with rain events or logistic issues, we can't get into the field and make an application on time. So a lot of times when we're trying to make that 1x rate application on Palmer amaranth and the way that it grows, or water hemp, a lot of times we're spraying a 2-foot weed. So they're in the grower's mind, maybe they're thinking, all right, now I need to use that full rate to control a 2-foot weed. But again, we got to remember that full rate is for a 3 or 4 inch weed, not a 2-foot weed. So actually, we're actually exposing that large weed to a sublethal dose, and it will go on to produce seed, just like I talked about with the smaller weeds. So just something to think about how herbicides don't really cause resistance, but it's the way we select for them that actually selects for those individuals that have the herbicide tolerance or resistant trait and go on to produce seed. So when we talk about seed production with Amaranthus species specifically, this was a study done by Sellers et al. In 2003. And what I like about this study is he did it in competition with soybeans. So we know with Palmer amaranth and water hemp, there's been studies that have shown that both of these weeds can produce up to 1 million plus seed per plant. But what's really important is to understand, in a field setting, in competition with soybeans, how much can they produce? Now, you see that they're still putting out 250,000 seed per female plant, still a bunch of seed going out. But just wanted to share the difference between some of the pigweed species that you probably have on your own farm in terms of how many seeds they can produce for a female plant. You also know there's several ways when we talk about water hemp or Palmer amaranth, you're talking about a seed that is the size of a period on a newspaper. So very hard. I'm looking at this combine cutting the beans here. Very hard to clean out a combine when you're talking about a seed that small to effectively get out every seed of the harvester. But they can also spread many different ways. Growing up, I grew up around the Mississippi River in Western Tennessee, and it tended to, whenever rivers got out real bad, that's when we would see new weed species or Palmer amaranth get introduced to new farms. There's been several studies. When I think of Canada, I think of waterfowl that migrate all the way through, say, the Mississippi Flyway, where they may be feeding and pick up Palmer amaranth or water hemp seed and spread it through places throughout North America. Huge problem there when we talk about migratory bird species. There's also, when we do plowing, mowing, harvesting, where the seed can actually get on the equipment, like I mentioned, much like with the combine, and spread that from field to field. But there's also cases where here in Ohio last year, a grower called and he had never seen Palmer amaranth before. It really wasn't well documented in this part of Ohio, but he mentioned that in 2015, he owns a dairy farm that they were in a drought and didn't have a good hay crop, so he bought a bunch of hay from Nebraska. And Nebraska is unfortunately a state that is full of Palmer amaranth, and you could tell from his hay barn where it started and actually introduced into his soybean and on into his cornfield. So that's just one example of how we as humans can move seed from place to place. But just wanted to go through how water hemp and Palmer amaranth can be dispersed throughout the landscape. Another thing that's important is to understand with water hemp and Palmer amaranth, there's so much diversity. Not only is it a dioecious species where we have both male and female plants, but oftentimes you can see in this picture, there's diversity within this picture alone. You see red stems, green stems. A lot of times we can see watermarks, plants without water milk. So there's a chance for, we talked about the competition in soybeans for 250,000 to 300,000 flowers to go out and produce an individual seed. So there's a lot of opportunity for diversity. But what I wanted to talk about here was, a lot of times, whether in places we pull into a field or along ditch banks where we don't manage our weeds as effective as we do in the crop, is we'll have water hemp come up in flushes and put on a seed head, which is nothing out of the norm. But there's been some studies done out of the University of Illinois that suggest, how the question they answered was how long after a male water hemp pollinates a female, how much longer does it take before we have a viable seed on that plant? And if we look to the left, when you see that dark, shiny coat on a water hemp seed, that's when you know that you have a viable seed. And the two differences between the A at the top and the B at the bottom are two different temperature regimes that we would have here in the U.S. and you would have in Canada as well. But the idea is here, 7 to 10 days after successful pollination, you will have viable seed on that plant. And Nick's going to discuss some ways to mitigate that, but it's just something to think about when you're going into 2021, how you probably need to differentiate the way that you manage the places where you pull into the field, ditch banks, etc., because seed is being viable seed will be available 7 to 10 days after that pollination. Water hemp does have a weakness, though. It is a great seed producer. We know it can get viable seed very quickly after pollination, but it does not live very long in the soil seed bank. So here's a study done out of Iowa State. But if you look at year one after introducing a bunch of water hemp seed into the environment, only 50% of that seed is actually viable, just due to predation from predators or maybe some environmental conditions that make it no longer viable. But if we go on to year 3 and year 4, you see the viability decreasing significantly. So there's ways that we can manage a farm and get ahead of this thing within 4 or 5 years. The problem is if our neighbor continues to neglect water hemp, or we use equipment that's been on a farm with water hemp and we continue to bring it back to a farm, that keeps us from doing this. But if we pay attention to those type things and have a great strategy going forward, we can get ahead of it. And I think it's also interesting, we talk about 4 or 5 years of viability of water hemp, but we look at weeds that we run into every year, like morning glory species or velvet leaf, where they have viability from 40 to 50 years. So what happens when water hemp is introduced into a farm? And this is an example that we use in the Midwest, but with the populations you now have in Canada, it's something to think about, or maybe something that you've actually seen. And it's a population shift. And this often happens whenever we have a very competitive plant that produces a bunch of seed like water hemp. So years ago here in Ohio, the main issues were Canada fleabane or horseweed or mare's tail and common lamb's quarter. And they would make up a huge proportion of the weeds that the grower was dealing with to control within a soybean crop. The problem is when something like water hemp comes into that environment, we've got to manage it differently. It can have multiple flushes through a season. We talked about it produces a number of seed, and it has unfortunately a great herbicide resistance profile, or an ability to become herbicide resistant. So what happens when a resistant water hemp plant is introduced to a farm? You'll see that you'll start being really good at controlling Canada fleabane and common lamb's quarter, but you'll see that your control tactics need to be changed, because over time water hemp will ultimately take over that field and be your main driver weed. thing to point out in the U.S., and you probably experienced the same thing in Canada, was 2019, the rainy season that we had. It prevented a ton of acres from getting planted. And unfortunately, this image to the right is a field that was neglected. And you probably can't tell through the image, but that is a field full of water hemp just going to seed. And Nick, my counterpart, always says, you know, in a situation like this, you get 1 year of seeding equals 7 years of weeding. So there's a lot of fields, unfortunately, that looked like this in 2019 and had significant returns of water hemp seed to the soil seed bank. So this is another way that we can have a population shift very rapidly when we're talking about something that produces seed that effectively. So what are the ways we can really get a head start of this thing? You know, I mentioned in the first slide, starting clean being one of those strategies. And I always show this slide, you know, why do we need pre-herbicides? This is a soybean crop that is within a Palmer amaranth field, if you will. And you can see the box where we apply a pre-herbicide. The main thing is how much selection pressure we are taking off of that post-application. So if you see where we applied the pre, you know, yes, we have really good weed control. And of course, there are some misses. There are weeds that are beginning to germinate due to that pre-herbicide breaking down. A lot of times growers refer to this as their pre is breaking and they have escapes that we need to control with a post-herbicide. So we can manage those weeds coming through that pre-herbicide application. What we cannot manage is where we neglect to put a pre and we have, you know, hundreds, thousands, millions of seeds germinating. With a plant, you know, at 4 to 8 inches can have 20 to 40 growing points. And often I tell growers here that there's not, you know, droplets big enough, there's not enough PSI, there's not enough carrier volume that we can put on a field to effectively manage a population like this from a post-application. So just something to think about, really the amount of selection pressure that you're taking off your post-herbicide chemistries by just using a pre. A lot of people understand how pre-herbicides work. When we spray a pre, we're obviously wanting soil activity, but you'll often hear your agronomist or your extension agent say you need an activating rainfall. So if we were to spray that herbicide on the soil surface and we didn't get a activating rainfall, it would just be active on the soil herbicide surface where you know, there's not many weeds that are going to germinate there. When we talk about water hemp and Palmer amaranth, we need an activating rainfall, but they like to germinate in that first half to inch of the soil layer. So that's where the weed seed germination zone would be, and we will control those weeds. Now you will notice that there will be some weeds that actually germinate if they're a larger seeded broadleaf, like a giant ragweed, that will germinate below that herbicide treated zone, and maybe they will actually get through that herbicide treated zone without being affected, and they'll actually come through the pre. But just wanted to put an illustration on how pre-herbicides work and why that activating rainfall is so important. So when we talk about weed management, and the two crops that are most common here in the Eastern Corn Belt are obviously corn and soybeans. And this is a slide that just really shows when each of the crops are very susceptible to weed competition. So in soybeans, there's been work done that says when we're around the V3 timing, right before we get into reproductive stage, that field has to be absolutely clean, because if we do have weeds competing with that crop, you will see a weed loss. And the same for corn. We know corn is a very competitive plant, but it has to get off to a start free of weeds, because if we do have weeds in the environment that corn is trying to germinate and it's trying to build that factory that fills the grain in that ear at the end of the year, this is very important for us not to have weeds interfering with that process. So there's ways that we've got to control weeds that aren't from a pre-herbicide. And you notice after harvest, that fall burn down is critical. When we talk about Canada fleabane, horseweed, In some places in the U.S., oftentimes after harvest, water hemp and palmer amaranth, it's still warm enough for that to germinate. So we have to do a fall application to control those weeds. But one of the reason I put this slide up is one of the ways to extend weed control in both crops is not only from a post or foliar application, but something we do in the U.S. is overlap residuals. And what that does is, we've talked about pre-herbicides already in this presentation, but over time, through chemical degradation processes, microbial feeding, that pre-herbicide activity will actually reduce down to a point where the herbicide breaks, like we mentioned, and you'll get a flush of weeds, and you've got to go and clean it up with a post. For example, we'll say glyphosate to clean that up. But what we've had to do in the U.S., specifically with weeds like water hemp and palmer amaranth, is include a residual herbicide within that post. And basically what that does is it gets your residual weed control or the soil activity back up to 100%. So we're controlling that water hemp or palmer amaranth as a seed as it's germinating, and not letting it become a weed to control with the post chemistry that we have very few sites of action left on. So it's something that's really caught on in the Mid-South when we talk about wider row spacing in crops like cotton and soybeans, where we're around 30 inches. And something that we've also done in corn with a 2-pass system is overlapping residuals to get effective control of those troublesome weeds, whether it's a grass or broadleaf. But really, when we get down to the grower level, this is what matters, what it costs the grower. And, the inconsistencies, whether a grower missed a pre-herbicide application or didn't have a timely post, there's a consequence of that, and it's money. And work done out of Iowa suggests that the inconsistencies that we have in weed control on average cost the grower $15 per acre, and that depends solely, obviously, on soybean price. But the more dense the weed density is, so the more weeds we have in that field, the higher that price goes, because we know the more weed competition we have with that crop, the more yield we're ultimately reducing. So something to think about whenever you're setting up your weed management plans. For something else I wanted to show is just an image of a pre-herbicide treated portion of a field versus a non-treated portion of a field, and just to put some numbers behind why we spray pre-herbicides. We've got 2.6 million plants per acre that we're going to have to rely on our post chemistries to control in the example on the left. Whereas if we use an effective pre, we're only dealing with 4,000 weeds controlling with the post. So you see the difference in selection pressure to our post chemistries. And I think it's really also important to understand how long our residual lasts in a soybean crop, because there's so many options that we have to use pre, but the idea is we want to use effective sites of action with residual products that have a longer half-life in the soil. So this is a study that we did at the University of Illinois, and basically we counted the number of days until we had a 4-inch water hemp. So you can see with the red bar, the non-treated plot, after planting, it only took 18 days until we had a flush of water hemp that was ready to treat at 4 inches tall. Where we utilized pre-herbicides, we see common herbicides like dual magnum, metribuzin. The premix of those is Boundary in the U.S. We look at Anthem or peroxysulfone and Authority by itself. You see we're getting longer activity compared to the non-treated check. But what I wanted to point out is when you take a great herbicide like peroxysulfone and put it with one of the best PPO pre-chemistries on the market, sulfentrazone, and apply that as a premix. Here in the U.S., we have access to Authority Edge. In Canada, it would be very similar to Authority Supreme. You see that we're almost doubling the amount of time where we didn't put a pre, and we're getting almost a week longer compared to other herbicide pre's on the market. So with that being said, the high soil seed banks is really the driver behind water hemp management. When we think about weed control, unfortunately, 95% control is now considered a failure, whereas we look back in history, that was a really good thing to have, but with something that produces this many seed and has a great resistance profile, 95% is just not enough. Multiple flushes throughout the season. Like I mentioned, we're dealing with this pest from planting all the way in some places in the U.S. to well after harvest. And, you know, there's this opportunity when we've got something as diverse as water hemp is the chance for failure with new technologies is just absolutely there. And we're seeing it right in front of our faces, as I mentioned in the beginning of the presentation, with dicamba being one of those that's no longer effective in some parts of the U.S. And now we have a population in the U.S. where Liberty or glufosinate is not working on Amaranthus species. So at this time, I will turn the presentation over to Nick, and he will implement some information on strategies to control this weed.
Alrighty, thanks Drake, and great job with that information. So really what you talked about leads me into this particular study that's going to kind of help us picture soil seed bank management practically. So this experiment demonstrates the impact that layered residual herbicide treatments can have on the soil seed bank over time. So one of the objectives for this study was to determine the effect of employing multiple herbicide sites of action on the number of viable specimens in the soil seed bank. And we accomplished this by taking soil samples from each respective treatment for grow outs. And as we look at the treatment list here on the x-axis, on the left-hand side, basically we have a residual application in the pre and post-treatment. As we move to the right, we have pre-residual followed by post alone, post plus residual, and then post alone. And so when we think about the resistance profile for this site, it did encompass glyphosate, PPO, and ALS resistant biotypes of water hemp. So before we initiated the herbicide treatments, we collected soil samples from each respective plot area, homogenized them in a bucket, and placed those samples into trays. And the picture on the right-hand side of the screen kind of demonstrates how we grew these specimens out in the greenhouse. So the red bar is actually the baseline grow out, and this was collected prior to starting the study, which provides us a benchmark to compare to. Next slide, please. So as we move ahead to the grow outs that occurred after only 1 year of herbicide treatment, and we evaluate the number of viable specimens that were recorded, you'll notice that the only treatment that reduced the number of viable specimens in the soil over this period of time was the layered residual approach. And so as you look at all the other treatment regimes, there was a profound increase in the number of viable water hemp plants. So this slide illustrates the importance of layered residual applications for sustainable control of our amaranthus species, such as water hemp or Palmer amaranth. When we think about it practically and we kind of omit those residual herbicides, it will secure our future production costs in managing those weed flushes, and it's also going to add to higher weed densities, which will compete with the crop for vital resources that would otherwise optimize our yield, and also expose more of those individuals to our post applications, which is going to increase the risk of selecting for resistance, just as Drake mentioned. Next slide, please. So this is some data that was actually conducted in 2009 and 2010, and so the prices don't really reflect what we're up against today. But just to set this slide up, there are 3 different management levels encompassing 1, 2, and 3 effective sites of action. So the vertical axis on the left is a metric for yield in bushels per acre, and the vertical axis on the right demonstrates water hemp density per square foot. So the blue bar indicates our overall yield, and the red filled circles represent the water hemp density. So higher blue bars and lower red dots would illustrate improved water hemp control and overall profitability through crop yield. And so if we look at situations where there's more of an upfront spend and pulling additional sites of action on water hemp, the density was lower at the end of the season, our crop yield was higher. So often we get in situations where we try to save money up front by using setup rates or no residual at all, and we follow with our foliar treatments, which often might not be as effective due to weed height at the time of application, which of course is going to influence our coverage, as well as other factors, and it may require an additional application for follow-up, and that's going to cost us more money in the long run. So from a grower investment perspective, as we incorporate residual treatments, it will increase our production costs, but hopefully this data kind of helps depict that in the long term, it's worth it. So next slide, please. So this is some work that was done by Dr. Ken Smith at the University of Arkansas, and basically we're looking at Palmer amaranth at varying heights and the respective exposure to different rates of dicamba, so 280 and 560 grams acid equivalent per hectare. So as we think about that blue bar, that is our field use rate for the low volatility dicamba concepts that are utilized within the extend type of trait systems. And what we see with dicamba is that once we get into those larger plants, 4 to 6 inches, you start to see both of those application rates slip in terms of activity. So click one more time for me, Drake. All right, so this is kind of an indication of what we noticed the first year we had the dicamba technology at our fingertips. Oftentimes we made that application and we looked over the canopy and we thought we did a pretty good job, but as we peeled that canopy back, we noticed that these plants were wrapped up below that canopy and they weren't completely dead. And so over time, these plants were able to go ahead and produce seed. And of course, that is representing a low dose type of exposure, and that could select for resistance over time. And we're starting to see that in areas of the Midwest and Mid-South, just as Drake mentioned. Next slide, please. All right, so we're looking at data that was generated by Purdue University that illustrates the importance of proper use rate selection in addition to timely applications on mare's tail or fleabane in terms of our weed height to optimize success with our herbicide treatments. So as we set this slide up, the columns on the left-hand side represent the use rate, and those on the right-hand side depict the % growth reduction by respective weed height. So what we notice is the higher use rate applied at an earlier growth stage allows the greatest growth reduction. And so the take home is, whether we're targeting water hemp or Canada fleabane, spraying smaller plants and utilizing the proper use rate is going to be a driver for effective control. And so by employing those residual herbicides, it's going to provide some cushion to be timely with those in-crop treatments of whatever chemistry your soybean trait system allows. And just as a general rule of thumb, we always recommend treating fleabane prior to bolting, which is going to increase our chances of controlling those populations. And by utilizing that residual treatment, again, it's going to allow us to have a little bit more flexibility in that post-application. Next slide, please. All right, so this is some work that I did at one of my sites in southern Illinois, close to Mount Vernon. We actually have a Palmer amaranth population down there. And so the y-axis depicts our % control, and then we have weed heights listed across the x-axis. So this is a situation like what many of our growers are up against with their post-treatments. Oftentimes they are distracted by maybe a weather event that doesn't allow them to get in the field, or perhaps they're side dressing corn. There's just a lot going on and a lot of multitasking that has to happen. And what we notice is when we get into those larger plants, we're not as effective, particularly with our contact herbicides such as our Liberty, or even situation where we're utilizing the diphenyl ethyl herbicide. So what we notice in these scenarios where we have larger plants is that we're more likely to take out that terminal growth, and it selects for the axillary buds to regrow. And in many cases, this is going to require an additional application and increase our selection pressure, which over time could result in resistant biotypes. Next slide. So this image illustrates how quickly a pigweed plant can grow after a failed trip with dicamba. And so this could facilitate an opportunity for these plants to produce seed and carry that inherent herbicide tolerance. So generally speaking, when we talk about foliar herbicide use across trait systems, the active ingredient should be applied to very small weeds, so preferably less than 4 inches in height. And I think this depicts the importance of utilizing residual herbicides ahead of planting from a resistance management perspective, but also to provide more flexibility and allowing smaller weed heights at the time of that post-application. So this rapid growth characteristic that Palmer amaranth and water hemp also encompasses will facilitate pigweeds growing off-label. And we know that large plants have more potential to withstand that herbicide treatment, and that's contributed to the evolution of herbicide resistance over time. Next slide. So where we stand right now, water hemp has evolved resistance to 7 different sites of action, and this presents a challenge to contemporary weed management systems because historically when one particular herbicide lost efficacy, we simply switched to a different mode of action. However, with multiple resistance, it complicates this system because we may not have a foliar option, and we very likely could see reduced activity for certain soil applied chemistries from these families. So I think this illustrates the importance of adopting diverse weed management plans with effective herbicides, also implementing those cultural tactics, and really focusing on that zero tolerance policy for weed escapes. I wanted to take a minute to discuss the different types of resistance to set this slide up. So those being target site resistance and non-target site resistance. With target site resistance, it's due to a mutation of a specific enzyme in a plant where the herbicide binds, and so the herbicide can no longer attach to that enzyme, which allows the plant to survive. As we think about non-target site resistance, it's more of a catch-all, so everything but an enzyme change. It could be plant architecture, cuticle thickness, compartmentalization of the herbicide, or even metabolic resistance. And so this slide kind of illustrates the chronology over time, showing the different resistance mechanisms discovered in water hemp. And a key point to take home from this slide is that up to 2011, 4 of our 5 resistance mechanisms were due to target site changes, and since then all new mechanisms of resistance have been non-target site based or metabolism based. So for the 7 sites of action that water hemp has been confirmed resistant to, 6 of them encompass known non-target site resistance mechanisms, and only 4 have been confirmed for target site resistance. So we're starting to see a shift in terms of the mechanisms of resistance to more metabolism based. And so if we think about this practically, this type of resistance might involve similar detoxification pathways that tolerant crops are using. So when we think about like corn and how it metabolizes off atrazine or the HPPD inhibiting herbicides, water hemp is utilizing similar processes. And so that can be pretty scary, but keep in mind that just because we have resistance to a specific herbicide in your field, it doesn't mean that every plant is going to confer that same resistance profile, and it should highlight the importance of tank mixing multiple sites of action with each trip that we're making across the field. Next slide, please. Okay, so here we're looking at basically the progression of herbicide metabolism in crops or weeds. So when we talk about this, it's always a crowd pleaser, but I think it's important to mention, as we discuss metabolism-based resistance in water hemp and Palmer amaranth. So if we think about, employing that herbicide initially, we have the parent compound, which is toxic to the crop, and we move into phase 1 of metabolism. We have several different biochemical processes that influence the parent structure. It could include hydrolysis or oxidation or reduction. And of course, this is changing that structure, which makes it less toxic. As we move into phase 2 of metabolism, we're starting to get into sugar conjugation. So again, attaching these groups to the parent molecule that's going to change that structure and minimize the toxicity or even make it non-toxic. So as we move into phase 3, that's where we get into secondary conjugation and incorporation into the cell walls, or even pumping that metabolite into the vacuole. So at that point, the herbicide is no longer toxic to that weed. Next slide. So when we think about the key players in terms of detoxifying herbicides, you can see there are several different mechanisms that may alter the parent herbicide structure. When we consider the primary mechanisms for seeing more of the metabolic resistance in our pigweed species, we refer to the cytochrome P450 genes quite a bit, as that type of resistance has been documented pretty frequently. But as you look across these different players, you can see that it gets pretty complex, as there could be over 1,000 genes contributing to the breakdown of these herbicides in the plant. Next slide. So this is a mode of action screen that we conducted on a water hemp population in central Indiana. And so the weed heights did vary, and many did exceed the labeled height for the herbicides we were utilizing. But this is a practical representation of what often occurs in the field. So basically, we evaluated active ingredients from 4 different commonly used foliar sites of action, those being the group 2, 4, 10, and 14 herbicides. And what we notice is that even when we look at some of the newer formulations of dicamba or 2,4-D in addition to Liberty, which we really are relying heavily upon to manage our pigweeds post-emergence, they just aren't getting it done, especially on some of the larger weeds. So I think this slide illustrates the importance of incorporating those residual herbicides with 2 effective sites of action to start clean and finish easier, especially in those areas where we know we're going to struggle with those post-applications. This is really what we want to avoid. And so if pigweeds escape our herbicide treatment, they're not only contributing seed back into the bank to secure future problems, but they're also robbing resources from the developing crop, which is going to influence our overall profitability in terms of robbing those resources and influencing our yield. So if these plants escape our post applications, in many cases there really aren't any other option to clean the fields up. And so in order to get ahead of pigweeds, it does require a zero tolerance approach, and the only option to limit seed return is to hoe these plants out and carry them from the fields. So in many cases in the past, our growers have decided to save money and chose not to add those residual products throughout the season, and that did result in weed escapes, and several ended up paying for roguing crews, which added to their production costs exponentially. Next slide. All right, so what about new chemistry? In the heyday of discovery, there were anywhere from 18 to 20 companies actively working to find new AIs, and at the onset of the Roundup Ready technology, many companies merged or exited the discovery business because it just didn't pay to invest due to that broad scale adoption of the glyphosate technology. So currently there are 5 different companies in herbicide discovery, and FMC is very fortunate to be participating in this space. But I think this slide stresses the importance of keeping the current tools we have effective, as we don't anticipate seeing a new set of action for pigweed control in row crops for at least the next 5 years. All right, so now we're looking at kind of a timeline of a discovery of different active ingredients and sites of action. And really the take home is the newest technology that we are working with in row crops are the HPPD inhibiting herbicides, and they're over 30 years old. So I think this slide depicts the importance of doing the best we can to keep the current tools effective and bridge that gap until we see that next new site of action. As we think about some of the concepts that we wouldn't necessarily pour out of a jug, this is some work that Dr. Bradley did at the University of Missouri, but basically looking at our late season water hemp density in plants per 6 meters squared. And he looked at several different tillage regimes here. And what we notice is that we do have statistical separation with the deep tillage event or moldboard plow, as well as conventional tillage when we compare that back to a no-till type of environment. So deep tillage can be very effective. Often it's hard for us to get our growers to kind of dig those moldboard plows out of the fence line and utilize them. And also our farm sizes keep increasing. So in many cases, it's just not feasible due to time management. But it can be an effective option for burying the small water hemp and fleabane seeds. But one thing to keep in mind is that when we do implement that deep tillage practice, we can only do it 1 year, because the next year we employ that tillage, we're going to bring that seed right back up to the soil surface. But as we think about our conventional tillage type of mechanisms, we're using metal to manage more of those weed flushes and relying less on those herbicides. So that can certainly be an advantage. And as we look at a similar metric here for row spacing, again, looking at our late season density in plants per 6 meters squared, what Dr. Bradley looked at is 30, 15-inch, and then drilled row spacing. And what we notice here is we see a drastic reduction in terms of the number of specimens late season just by narrowing our row spacing up. And so when we think about that narrow row spacing, it is going to provide more competition between the soybean plants, and that's going to allow them to have longer internodes, reach canopy quicker, and shading that soil surface can be very critical for managing our pigweeds late season, because really all they need is a flash of light and any bit of soil moisture, and that will germinate them. So along the same lines here, we're looking at late season density, plants per 6 meters squared, and the respective planting population. So what he did is he looked at several different treatments, 130 on up to 220,000 plants per acre. And what we notice here is once we get up to that 160,000 plant per acre seeding rate, which if my math is correct would be close to 400,000 plants per hectare, you see a pretty significant reduction in the number of water hemp plants late season. So again, getting back to that interplant competition, really allowing longer internodes and a quicker canopy is going to help us manage these weeds late season. So what about cover crops? And I think this slide illustrates that they can be effective management tools for suppressing summer annual weeds. And as we set this slide up, we have several different cover crop species listed on the y-axis and the relative summer annual weed emergence on the x-axis. So what we notice is that many of the more dense species such as shea rye and wheat that quickly reach canopy could provide greater levels of suppression than a traditional burn down treatment of glyphosate and 2,4-D. So in areas where we have shorter growing season, such as Canada, often it's very difficult to establish the cover crop after that cash crop is harvested. But I do think this data makes a case that utilizing cover crops within an integrated weed management strategy can benefit control, but it does require balancing species selection in addition to planting date to be effective. Next slide. So this is the question that we face each season. Many times escapes are evident just prior to harvest, and no weed scientist is going to be able to look at this plant and tell you what the resistance profile might be. But they can assure you that this female plant will contribute to the soil seed bank and carry whatever resistant allele she has into the next season and beyond. So I think it highlights the importance of practicing zero tolerance for seed return in order to keep that seed bank static at the very least, and set the stage for effective management in the coming years. So many growers used to kind of leave this plant in the field, and now they're sharpening their hoe and removing it from the field and carrying it out. So in certain areas, I've heard this being referred to as pig hunting. So, load up the cooler with your drink of choice and hop on the side-by-side and send your poor children after these guys to hoe them and remove them from the field. Okay, so we're just going to kind of reiterate some of the key points that we've hit on in terms of resistance management, and really holistically what we're trying to do is reduce the soil seed bank over time and manage our weed species long term. And the way to do that, certainly putting our best foot forward, would be starting clean and finishing easier. So utilizing that strong foundation pre-emergence herbicide to minimize the number of escapes that might occur and reduce the selection pressure that we're putting on our post technologies. So we certainly want to maximize our diversity and our weed control practices. So this is going to encompass rotating our crops, traits, and chemistry. And keep in mind that when we rotate our crops, inherently we are going to have more diversity in our herbicide program. So it kind of goes hand in hand. Definitely want to utilize multiple modes of action within that crop, especially focusing on those tank mixtures with 2 effective sites of action with each treatment that we're making. I mentioned point C there in terms of the modes of action with different crops. Definitely don't want to cut our rates and apply timely, so 4 inches or less, or maybe even making that layered residual application before the next flush happens to manage these weeds as seeds versus plants where they're more vulnerable. And so we definitely want to incorporate those pre-herbicides into the system. That's going to allow us to have more cushion and making our post applications more effective. Maximize our crop competition. We talked about how to do that through narrowing our row spacing and maybe increasing our seeding rates. Sometimes this conflicts what several of our agronomists are telling us. Many times they'll say, hey, in soybean, you only need 100,000 plants per acre and you've optimized your yield potential. We agree with that, but if you're dealing with fields that traditionally have had high levels of weed densities, we can incorporate those types of concepts in terms of narrow rows and higher seeding rates to help us in terms of managing our weeds. We want to integrate our non-chemical practices where feasible. So we talked about, mechanical options, cultural practices, as well as cover crops where it might be feasible, and really focus on zero tolerance for escapes. So, that might mean going out and hoeing those plants, carrying them out of the field like we mentioned, but there's also some pretty interesting technology that's being developed in Australia for the management of ryegrass, which has basically become resistant to every herbicide they're using over there. But they're using seed destructors. So basically it's an attachment that goes right on the combine, or might be pull type, and basically the chaff goes through a hammer mill, which can devitalize the weed seed that moves in that chaff. And that's certainly something to think about. But what they're noticing in some areas is that Mother Nature always finds a way. So they're selecting for ryegrass biotypes that actually shatter at the head versus moving through the machine with the chaff. So there's always, something to think about, and the weeds seem to be a step ahead of us, but certainly we have to incorporate all these different practices in order to be sustainable with our management.
That concludes our FMC Tech Talk, a lesson from our neighbors. I'd like to take this opportunity to thank our speakers, Drake Copeland and Nick Hustetti, for some great information on herbicide resistance today. I'd also like to thank you for taking the time to sit down and review this webinar. Please keep an eye out for future invitations on FMC Tech Talks, and have a great day.